Hello everyone, my name is Nosan Ghafourian, and in this talk I would like to present our paper on gambling adversarial nets for hard sample mining and structured prediction, application in ultrasound thyroid nodule segmentation. Many machine learning problems exhibit long-tail distributions among different label classes and input representations. Scarcity of certain pathological processes gives this a further significance in the medical imaging world, and especially in medical image segmentation. From a more generic perspective, even within the samples of the same class, not all samples provide the model with the same level of new information during the training. Therefore, treating all the samples the same way might end up in slower and less effective training procedures. To cope with this issue, different methods have been proposed in the machine learning community that can be generally categorized into the sampling manipulating approaches and cost-sensitive ones. Let's now focus a bit further into the latter category. Consider a semantic segmentation task with the most commonly used category called cross-entropy loss, where by default each sample is treated identically. A cost-sensitive training would break this assumption by introducing a weighting function over the training samples, which in this case are each individual pixels or voxels. In the simplest and most frequently used form, the weighting function maps every sample to a constant number inversely proportional to the frequency of the corresponding class, where the class scarcity is used as a proxy for its difficulty. Focal loss improves over this by taking the prediction error as a possibly better heuristic for estimating the difficulty and importance of the samples. Adversarial confidence learning, a recently introduced approach, aims to leverage a discriminator to estimate the density of the predictions in the distribution of ground truth annotations, and use that as a clue to outweigh the samples with higher uncertainties. As we will come back to this shortly, all the aforementioned methods suffer from certain shortcomings, which we aim to address by incorporating gambling adversarial nets that learn to highlight harder samples. Adversarial semantic segmentation is another closely relevant topic to our work. Comparing the samples shown predictions made by a unit trained with a pixel-wise loss with a corresponding ground truth masks, we see that there are certain high-level structural qualities in the labels that are lacking in the predictions. This hints toward insufficiency of independently formulated per pixel loss terms to preserve such qualities. With the advent and success of GANs, the adversarial training framework has been adapted and used also for semantic segmentation. In this setup, with the goal of preserving higher-level structural qualities, a discriminator is incorporated to make a high-level sanity check of the formations of per-sample predictions altogether by matching the distributions of real annotations from human beings and fake ones made by semantic segmentation networks. The adversarial loss being added as a regularization to the pixel-wise loss can be formulated with a conventional GAN cross-entropy loss, or alternatively with distances between real and fake distributions in an embedding space. However, as we argued, there are certain problems with adversarial semantic segmentation set up as such. One major issue is an inherent ease in discrimination using only low-level cues. For instance, as illustrated by the sample on the left, the discriminator can perfectly distinguish the fake and the real samples by just noting a single pixel value prediction, where the image with the soft prediction is obviously fake and coming from the network, and the one with crisp zeros and ones probability vector is real and coming from the human annotations. Discrimination on such low-level cues result in more serious issues that are: first, encouraging the model to fake to be certain and predict probability vectors that are crisp, as shown in the previous work, where the average predicted likelihood grows much more quickly to proximity of 1 in adversarial training. And second, the sufficiency of such easy to acquire low-level cues hinder the discriminator to provide feedback on the more useful high-level consistencies. Stepping back and analyzing the situation, we find it still useful to incorporate a critic that provides feedback on interpixel prediction relationships and their structural qualities, while we wouldn't mind soft prediction values such as 0.87 as long as the predictions are correct. The main idea of gambling adversarial nets stems from these key observations. The critic operating on holistic prediction views is still kept, but the conventional fake-real distinction task is reformulated into a wrong-correct recognition. To implement all these, the critic becomes a dense prediction network that, given the input image and the dense predictions, from the semantic segmentation network predicts how likely predictions at each location is wrong. We call this the gambling map. But how is the gambler trained to predict such incorrection likelihoods? This is done by using those likelihoods as weights for the per pixel loss and formulating the gambler's loss to maximize the weighted pixel-wise loss. To minimize this, the gambler needs to maximize this sum of products, which is achieved when the two terms that are the gambling maps and the per pixel loss are highly correlated, meaning that the gambler has to give higher response to faultier predictions without directly knowing about the true labels. While the gambler attempts to find structurally bad predictions as clues to detect mistakes, we enter the semantic segmentation model in a minimax game with it, aiming to expose those clues as least as possible and minimize its weighted cross-entropy loss. A trivial degenerate solution is when the gambler infinitely bets everywhere, which gives a global minimum to its loss. To avoid this, we impose a limit to the total amount the gambler can bet on all samples, implemented via a spatial normalization. This makes the analogy to a real-world gambler complete, as the gambler network now needs to think twice before spending its limited budget to gamble. To test these hypotheses, we use data from the TN-SCUI challenge, where the task is to perform thyroid nodule segmentation on ultrasound images. We compare the gambling adversarial networks to the commonly used cross-entropy as well as the mentioned literature on the adversarial training and cost-sensitive learning that are the normal adversarial training, SEGAN, focal loss, and confidence adversarial training, while preserving the setup identical and only adjusting the corresponding loss terms accordingly. We compare the training scheme on three state-of-the-art semantic segmentation models, namely the UNet, PSPNet, and DeepLab v3+, where the reported metrics are averaged over 3 independent runs. As for the metrics, apart from the commonly reported DICE and Jacquard indexes, we also measured metrics that better correlate with the structural qualities of the predictions, namely the Hausdorff and Schoenfeld distances and the BF score representing the aggregated distances and F score on boundaries. On all the three aforementioned architectures and across the different pixel-wise and structure-based metrics, we found consistent improvements over the compared methods. Besides, to evaluate our hypothesis that gambling nets do not encourage the models toward faking to be certain, we computed the mean maximum class likelihood representing the average confidence for the predictions, and we indeed observed that the gambling nets increase the model confidence significantly less than the conventional adversarial training schemes. Here we provide a qualitative comparison between the different methods on a number of samples, where the two reported numbers in red are the DICE score and the Schoenfeld distance respectively for each prediction. Please refer to the supplementary materials for extensive qualitative comparisons. Let's now further highlight some of the major consequent differences between the gambling nets and the previously mentioned relevant literature. When compared to the focal loss, we can see the gambling nets as a learning-based version of the focal loss that in contrast extracts the weights from the labels. While both models backpropagate the weighted loss through the illustrated path A, gambling nets offer an extra backpropagation path illustrated as B, going through the gambler, providing a structural information on why the gambler has selected certain locations to gamble. Furthermore, noisy label scenarios are quite troublesome for focal loss. However, not reweighting the samples directly based on the noisy labels gives better robustness to the gambling nets comparably. Finally, the confidence adversarial learning seems quite similar to the gambling nets in the first glance in the sense that they both use adversarial training for learning the weights. However, the adversarial confidence learning keeps the conventional real-fake discriminating discriminator and inherits the same drawbacks. Unlike the gambling nets, the discriminator is given the same fake label for the whole fake prediction, which encourages the discriminator not to localize the error patterns and to propagate the fake predictions throughout the whole image. Therefore, despite our attempts on tuning the confidence learning, we found it difficult to achieve non-uniform uncertainty patterns from the discriminator as illustrated in this figure, comparing the weighting maps from the confidence adversarial learning to those from gambling nets. To summarize, in this work, we demonstrated a successful usage of gambling adversarial nets for a medical image segmentation task. However, we believe the idea of learning the sample weights in a cost-sensitive setup via the gambling nets can be useful in a broader set of visual recognition tasks.